Hello everybody and welcome to the review packet for Cumulative 15, and this is video 3. We're going to be starting here with number 22. And the directions for this is to solve the quadratic. We can pick any method we'd like. So if I looked at 22, I noticed that it's not equal to 0. So the first thing I want to try is maybe completing the square. So if I divided everything by 2, I would get an odd middle term and a fraction. So I'm thinking that's not the best method. What I'm thinking may be a good method is quadratic formula. If we add the 5 to the other side, I could check to see if it factors. I could do split the middle term, but why not use the quadratic formula because we haven't yet, and it's good review. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. So x would equal negative b plus or minus the square root of negative 10 squared minus 4 times 2 times 5 all over 2 times 2. So if I continue with that, I get x equals positive 10 plus or minus the square root of negative 10 squared, which is a positive 100, minus 4 times 2 times 5, which is 8 times 5, or 40. There are not two negatives here, so this does not change to a plus sign, all over 4. X equals 10 plus or minus the square root. 100 minus 40 is 60, all over 4. So that would be x equals 10. Now we can't take anything out of these three numbers yet until we split 60 into perfect square and not. So I'd have plus or minus, the biggest perfect square that goes into 60 is 4, or 4 times 15, all over 4. X equals 10 plus or minus 2 root 15, all over 4. Now that I have these like terms, I'm allowed to reduce that triangle by taking a GCF of 2 out of all of them. So my final answer in exact form would be 5 plus or minus 1 root 15 all over 4, or just 5 plus or minus root 15 over 4. Now this answer again is in quote-unquote exact form. If you would like to find the decimal answers, you definitely could. You could do 5 plus root 15, enter, divided by 4, and you would get 2.22. And then if you did 5 minus the square root of 15, enter, divided by 4, you get 0.282. So it is possible to get the decimals as well. That should be a decimal there. And this is especially helpful for when we're graphing quadratics. Back up to the original problem. That took a while. If we look at 23, we want to figure out which method we think is best. Because it is not equal to 0, I'm thinking maybe completing the square would be best here. And another reason I think it might be good is because our b term is even, which makes our b over 2 squared method a little better. So let's do this one by completing the square. Doesn't hurt to review. If I want to, there's no number in front of x squared, so I don't need to divide by anything. So the first thing I'd have to do is add that blank number on both sides of my equation. That should be squared. If I take b, negative 4, divide it by 2 and square it, that's really negative 2 squared, or positive 4. So when I add 4 on both sides, I get 24 over here. And then this side, this always ends up being something I can factor. This ends up factoring to x minus 2 times x minus 2, which is really x minus 2 squared equals 24. The reason we do this is because this problem does not factor, so we're forcing ourselves to use square roots instead. So now, if I take the square root of both sides, these cancel, and I'm left with x minus 2 equals plus or minus root 24. And the reason we need this is because it is a quadratic function. There are two answers usually. So I have x minus 2 equaling plus or minus, might as well reduce the 24. I'm going to split that into 4 and 6. So I have x minus 2 equals plus or minus 2 root 6. And if I finally want to solve for x, I would add 2 on both sides and get x equals 2 plus or minus 2 root 6. And even though it looks like it here, we cannot add these because this does not have a radicand or a radical of root 6. So this is, again, my answer in exact form, but you definitely could find the decimal answers as well if it's asked for. If you do 2 plus 2 root 6, that is 6.89, or almost 6.9 exactly. And then if you do 2 minus 2 root 6, that is negative 2.89, or almost negative 2.90 exactly. Moving on to radicals, which is unit 10. We want to either add, subtract, multiply, or divide these radicals. And so if I look at 24, my goal is to split this into perfect squares and not. So I want to make my perfect pile and my non-perfect pile. Remember, in order for an exponent to be perfect, it has to be an even exponent. Numbers we treat like we've been treating everything else. If I look at 108 and I think about the numbers that divide evenly into 108, specifically perfect squares, through trial and error, I realized that the largest perfect square is 36. So 36 times 3 is 108, and 36 would go in my perfect pile, and 3 would go in my non-perfect pile. X to the 9th. Now I purposely put this here because of things I've noticed on past tests. It's tempting to say that x to the 9th is perfect because the number 9 is a perfect square. But if an exponent is not perfect unless it's an even number. So unfortunately, we'd have to split x to the 9th. We'd have to split that x to the 8th times x, because we want the largest even exponent next to 9. Same with y to the 7th. We would put 6 y's over here and the remaining y over there. And then finally, z to the 12th is perfect because it's an even exponent. So z to the 12th would go in the first pile. And then once I figure out what my piles are, I can reduce this first perfect one. Square root of 36 is 6. The square root of x to the 8th is x to the 4th, because you're really dividing the exponents by 2. Y to the 3rd, z to the 12th would really be z to the 6th, root 3xy. So this is my answer for number 24. 25 is asking you to divide the two numbers. However, I noticed that everything is underneath the square root, and if you would like, you could make this root 36 x to the 4th over root 4. The reason I like this problem so much is because every single thing is perfect. The square root of 36 is 6. The square root of x to the 4th, because it's even, is x squared. The square root of 4 is 2. And so this answer is almost reduced, except I can divide 6 divided by 2. So my answer just ends up being 3x squared. Number 26 is asking you to rationalize. At the bottom we have 4 times root 2. We don't have any plus or minus signs. So what we could do to get rid of the radical is multiply top and bottom by root 2. And if I do that, I would end up with 10 root 2 on the top, not root 20, because these both don't have radicals, over 4 times root 4 technically. So I'd have 10 root 2 over 4 times just 2, because the square root of 4 is 2, which would be 10 root 2 over 8. And then if I reduce 10 and 8, I can take a 2 out of both of those. So my final answer would be 5 root 2 over 4. Let me write that more neatly up here. 5 root 2 over 4 is your final answer for number 26. I purposely put 27 directly after 26 to show you the difference. This one, the 4 and root 2 are multiplying on the bottom. This one, 8 minus root 2 is subtracting. So this is the case when you would need the conjugate. And so you'd need to multiply top and bottom by 8 plus root 2. The reason the sign changes is because the middle term on the bottom will eventually cross out. So I'm going to distribute on the top. 6 times 8 is 48. 6 times root 2 is 6 root 2, not root 12. Then on the bottom, I have a parenthesis times a parenthesis, so I have to distribute or FOIL. 8 times 8 is 64. 8 times root 2 is 8 root 2. 8 times negative root 2 is minus 8 root 2. Negative root 2 times positive root 2 is negative root 4, technically. In the denominator, my two radicals combine to be 0, so they're gone. So I'm left with 48 plus 6 root 2 in the numerator. In the denominator, I'm left with 64 minus the square root of 4, which is really just 2. So I have 48 plus 6 root 2 all over 64 minus 2, which is 62. Just like the quadratic formula, I can reduce all three of these numbers by taking out a 2. And if I do so, I'm left with 24 plus 3 root 2 all over 31. Final answer, because I cannot take a 2 out of my root because it is not a like term. Now for number 28, my goal is to add these radicals. And if I do so, I need my radicand to be the same. But before we start, I did change this problem that I think for the better. So if you could star this one, if you could please put a 6 in front of the root 32. Okay. So now if I really want to add all of these radicals, because the radicand is not the same, maybe if I split these radicals into perfect and not, I can get them to match. So this first one, let's do 6 times root 32 is split into 16 times 2, plus 3 times root 50 can be split into 25 times 2, perfect square and not, minus 2 times root 9 times 2. So this becomes 6 times 4 root 2 plus 3 times 5 root 2 minus 2 times 3 root 2, which is really 24 root 2 plus 15 root 2 minus 6 root 2. Notice that all three of them now have a radicand of 2. So if I add 24 plus 15 minus 6, I get the answer of 33 root 2's remaining. So remember, only add things if they have the same radicand as a like term. Number 29 is asking you to distribute the 3 root 5 to both terms. So if I do so, I'm going to multiply things that look like. 3 times 2 is 6. Root 5 times root 5 is root 25. Then if I distribute this to 7 root 10, 3 times 7 is negative 7 is negative 21. Root 5 times root 10 is root 50. If I want to keep simplifying, I notice that 25 is a perfect square. This really becomes 6 times 5 minus 21. Now root 50 in the last problem, we split into 25 and 2. So let's do the same. We always want to reduce the radicals if possible. So I have 30 minus 21 times 5 root 2. If I multiply 21 times 5, I get 105. So I have 30 minus 105 root 2. And even though it's insanely tempting, please do not subtract these because this does not have a radicand of 2. So we are done with 30 minus 105 root 2. Moving on to radical equations, if I take a look at number 30, my goal is to get my radical alone. So the first thing I want to do is subtract 2. 6 root 2x minus 4 equals 18. I then want to get the radical alone, so I'm going to divide by 6. So I have root 2x minus 4 equals 3. Now I can't move either of these numbers yet because they're stuck under the radical, so why don't we get rid of the radical by squaring both sides? And if I do that, I'm left with 2x minus 4 equals 9. Add the 4 on both sides. 2x equals 13. And so if I take 13 divided by 2, I would get 6.5. So I think my answer is 6.5. If I would like to make sure, I absolutely can check myself. And so what I do is take the 6.5 and plug it back into the original equation. Do both sides equal 20? Well, 2 times 6.5 is 13. So we have 6 times 13 minus 4 plus 2 equals 20. 13 minus 4 is 9. So does 6 times the square root of 9 plus 2 equal 20? Or does 6 times 3 plus 2 equal 20? Yes, it does, because this is 18 plus 2. And so this is true, which means that 6.5 definitely works. I'm going to continue with numbers 31 and 32 on the next video. Thank you.